Today, our webinar titled Solving Formulation Challenges of Thermally Conductive Materials and E-Mobility. It's another one in a series really where we're focusing in on a lot of the materials related to thermal management of EVs and the sort. Today, I'm excited to announce that we will have a guest speaker, Joe Stoller, who is a senior R&D chemist from Epic Resins. He will be joining us here to go through a little bit of what they're doing at Epic Resins to kind of address some of these issues, and again, also available for the end Q&A session. So before we get into that, I will just give a little bit of a brief background, a little bit of an intro to who C-Therm is, what we do, just for those that may be new on the line here today. So here at C-Therm, really, we're all about simplifying thermal conductivity testing for the materials of tomorrow. Really, that's our raison d'etre. What we focus on here is instrumentation and methodology, all surrounding thermal conductivity. In particular, just as a kind of a note, our Trident platform, this is our flagship system. The system that was featured on that intro video there, if you were able to see that at the beginning. It features 3 different methods for thermal conductivity. Really, there is no one method that can do everything. There are, of course, certain limitations that you need to be aware of, whether it's related to your sample size, testing condition, things of the sort. Of course, some are more versatile than others. But again, really our Trident platform gives you the most coverage for all possible testing scenarios. And a little later on, Joe will be going into how they're using one of these methods in particular as it relates to thermal conductivity. So that's a little bit of background on the instrument. My colleague Len's also posting various links in the chat box. So if any of these pieces are of interest to you, definitely feel free to check them out if you want to get some more information. So this quote here, that this really just embodies the message I kind of spoke to earlier there, and really the idea behind Trident. So when all you have is a hammer, everything looks like a nail. Really the single largest source of poor data that we see out there, especially for thermal conductivity, is if you're taking a good method and applying it in a scenario that it just wasn't designed for. Again, all methods have certain limitations that you need to be aware of. But again, the idea with Trident is you're not limiting yourself to maybe using a method that's good for one thing and applying it in an area that's not so much designed for. Again, that's really just an adage that we like to focus on here as it relates to really the idea behind Trident. Now, with respect to thermal conductivity, whether it's the transient methods that we focus on or steady state, or maybe you're interested in both, there's a lot of options out there. We do have a method selection guide that's available as a free download. Definitely feel free to take a look at that if you want to learn about some of the methods that we offer and some of the others that are available in industry, where they play best, types of materials, things of that sort. But this really brings us to maybe a little bit more focus on what we're going to look at here today. Just wanted to cue up a little bit of a quick intro here before I pass it off to Joe. When we're looking at EVs, looking at electronics, battery systems, what have you, a lot of the time we're focusing in on ways of optimizing performance and avoiding these types of failure modes. The kind of quote here you can see, temperature factors account for about 42% of all faults in various electronics. There are other reasons, of course, they kind of note vibration, humidity, other factors there. But really the temperature aspect is what we're going to be focusing on here primarily. Again, as it relates to the thermal management, how well these systems can dissipate and handle the heat that's generated, to, of course, avoid things like thermal runaway, things of this sort. So, at C-Therm, there's really 2 areas that we're really focusing on in this industry in particular, both from really an R&D side and as well as in manufacturing. So when we talk about EV safety and performance, this requires effective thermal management. And really to obtain effective thermal management, this is built on optimized thermal conductivity. So again, whether it's at the R&D stage, product design level, really providing means of accelerating groups to be able to formulate faster, get feedback on those changes, and understand how they can make these improvements in a very tangible way. And we're also looking at focusing with groups in the manufacturing industry. So really from manufacturing, it's whether that's, process monitor and control, helping with scaling, really, traceability of material performance, things of this sort. So, there's different areas that we play in. Today, really, when I pass it off to Joe, we'll be going in on some more of that design level and a lot of the considerations that go into there. But, with that, I will end my little intro here, and it's my pleasure to be introducing Joe Stoller, again, Senior R&D Chemist from Epic Resins. Let me just go ahead and get this section started here.
Welcome, and thank you for joining us. My name is Joe Stoller. I'm a research and development chemist at Epic Resins in Palmyra, Wisconsin. Today, I'm joining you to discuss how thermal management in polymers and adjusting the thermal management of a polymer affects other properties and can influence those properties of the polymer. Before I get started in talking about thermal management in polymers, I want to talk a little bit about Epic Resins. Epic Resins' core chemistries that we work with are primarily epoxy and polyurethane thermoset materials. We've been in business for over 65 years. And we're an international company. We sell products all over the world. We have over 1,500 different customers around the world. We have over 3,000 different formulas that you can choose from. Additionally, we do custom formulating. So we can either do adjustments to those current formulas we have, or we can develop a brand new formula depending on your requirements for your specific application. We're located in the heart of the Midwest in Palmyra, Wisconsin. Just situated between Milwaukee and Chicago, you see on the map there. All of our research and development and our production is done at that facility in Palmyra, Wisconsin. In working with Epic Resins, you'll start off with one of our technical sales team. They'll start off by getting to know you and getting to know your application and really what you're looking to solve, what problems you're looking to solve in your application. From there, this is where it gets a little bit more unique with Epic Resins, is you're going to work directly with a chemist, either myself or one of my colleagues, to develop a product that suits the requirements of your specific application. We'll do that testing in-house from our multi-mass spectrometer, our NMR, FTIR. We have a number of different finished physical property test equipment that we'll use as well on site. So all testing is done on site. Additionally, we have prototyping capabilities here at Epic Resins. A number of different meter mix and dispense machine, vacuum chambers, so that you don't have to do any capital investment in order to figure out what processes that you need to do in your specific application. So to get really into what we wanted to come here today and talk about, we're going to first start off by talking really what is thermal transfer. A lot of people think of it as thermal conductivity, but there's a number of different ways that heat is transferred from one place to another. First and foremost, we'll talk about convection, right? We're all, we've all got that bowl of soup right out of the kitchen and it's too hot, so we blow on that, and that fluid of air blowing over that is convection, right? In water currents in the ocean, that's convection. So it's some type of media, some type of fluid, whether that's air or water, that's flowing within a system that's moving heat from one place to another. We can also think of radiators or radiators in thermal management systems in a car, where you're getting both convection and advection. Ultimately, a fluid or an air, a gas, pulling heat from one place to another. Now in polymers, this isn't a huge effect, right? Because it's a solid, so there's no movement that's happening. So only convection that would be an issue with polymers would be exterior to that, so in the thermal management system. Radiation. So radiation, we've all been standing in front of the window, soaking up the sun. We've been on the beach and felt that warmth of the sun. That's actually photon energy. That's an electromagnetic radiation. And that is a minor factor in polymers, primarily because most polymers will block infrared energy. That's a little bit depending on the filler type. Different filler types will have different levels of invisibility, if you will, to infrared energy. But for the most part, it's not a factor that we really consider too much when we're talking about polymers. Phase change. We're familiar with the old high school experiment where we understand how ice melts. Well, that's a phase change. And what you're getting is not only the energy that's required to heat up the solid ice, but also the phase change from turning it in from ice or a solid into a liquid. And you get a much faster molecular motion when that happens. You also get a much faster molecular motion when it goes from water to a gas. Now, obviously, in thermosets, we're not melting, we're not turning into a gas, unless you have a big problem. But we do have what's called a TG. So in thermal sets, we have this situation where as the temperature of the polymer rises, it will go through a phase change of its TG. And ultimately, the TG, and we're going to talk a little bit about this later in the presentation as well, but the TG is really the point at which a material, the temperature at which a material goes from a rigid glass material to a soft pliable material. And there's a little bit of extra energy that's absorbed during this transition. Again, it's not a huge factor. It depends a little bit on your operating temperature of your polymer, but not a huge factor when we're talking about thermal transfer in polymers. The real big section is thermal conductivity or conduction of heat. And really, conduction is all about kinetics. It's all about the contact that molecules have with one another and how those molecules are in contact with other things in a compounded system. So when we're looking at polymers, we're going to talk about fillers. There's ultimately it's particle contact, all right? And that particle contact is based around what's called a phonon. A phonon is an excitation wave of the particular molecules. And think of it kind of like a sound wave. We're going to talk a little bit about this a little bit more when we get into polymers. But one reason that polymers generally have a lower thermal conductivity than metals is because the particle contact isn't as uniform as it is in metals. So on the left, you see a little video of kind of a graphic representation of waves going through a polymer versus on the right, going through a metal or a mineral. So you see on the right, it's much more uniform. You have a much more consistent movement of those, much more intimate contact between those. That's going to conduct thermal energy or phonon waves much better than polymers will. And we're going to talk a little bit more about that in a minute. When we talk about thermal transfer in polymers, we do the analysis. Let's start off by talking a little bit about how we do this analysis. So we use an MTPS method, which stands for Modified Transient Plane Source. Now, C-Therm is going to be on this call in a little bit. They're going to talk a little bit about this method a little bit more. So I'm not going to go into the details of it. But here at Epic Resins, we've been using this for over 10 years. It's a great method. It's tremendously accurate. And it's a great tool for us because it really gets us to a finished product much faster. We can test thermal conductivity of a number of different samples, a number of different changes, and get results so that way we can modify those formulas and test again. Instead of taking many hours to run a test, it only takes a few minutes. So great piece of equipment that we utilize really to speed up time to market. We're talking about thermal conductivity in polymers. There's two different areas, right? We're talking about the polymer structure and also the mineral structure, the fillers that are used in there to enhance thermal conductivity. At Epic Resins, we formulate on a molecular structure to property relationship, right? So talking earlier about phonon energy and how it's really a wave traveling through the material, the efficiency of that wave is based on the polymer structure. We utilize our multi-mass spectrometer. to do that. Ultimately, a multi-mass spectrometer is a mass spectrometer that allows us to weigh molecules or understand the chain length of molecules. And we also utilize our NMR. Our NMR allows us to understand what the function of the shape, the different side chains of a particular molecule look like. So we can get a better understanding of what the chain and the polymer structure looks like. Because that's really important when you're looking at phonon wave efficiency. Phonon wave efficiency, they're much more efficient. Like we were talking about before, in polymers, if you have more disjointed movement, you're going to have lower conductivity than you are in, for example, a metal or a mineral, because they're much more uniform in shape and in its structure. So what structure is that, right? So it's number one, cross-link density, all right? So in the graphic here, cross-link density, the higher cross-link density, the more all of those molecules are chain linked together, the more they're in intimate contact. So a wave is going to transmit much more efficiently through them. Additionally, crystallinity. So it's not only cross-link density, but it's also how uniform is that cross-link density, right? So you see on the picture on the right, crystallinity, very uniform crystallinity, right? When you have something that's amorphous, or the picture in the center, you don't see much uniformity, you don't see a whole lot of cross-link density. So when you have more of an amorphous type of structure, you're going to have lower cross-link density, all right? I have a little graphic here to kind of show a little bit about that. So generally, polymers are going to be anywhere from 0.1 to 0.3 watt per meter Kelvin. On the low end of that, low cross-link density, low crystallinity, you're going to be about 0.1. High crystallinity, high cross-link density, you're going to be at about 0.3. Now, a lot of you guys out there that are really concerned about thermal conductivity are thinking, oh my gosh, that's very low. And it is. Now, we're talking just the polymer itself. We haven't talked about filler yet and how filler influenced thermal conductivity. But just having the understanding that when you formulate from a molecular structure to property relationship, we can squeeze out every little bit of thermal conductivity in the polymer that you might need for your specific application. All right? So, thermally conductive fillers. So, thermally conductive fillers is where the majority of thermal conductivity in a polymer comes from. And it's really important to understand how thermally conductive fillers affect other properties. And that's really the important part about what we're talking today, right? First, filler type. How do we choose filler type? Well, the filler type of a material is going to have lots of different properties, right? We have a number of very common fillers that are used in thermoset polymers. Now, not all of these are considered thermally conductive, but I want to give you a good understanding of the range of them and how they relate to each other with these different properties. Now, this isn't an exhaustive list. There's a number of other fillers that are used to improve thermal conductivity or improve thermal properties. You see them there under other fillers: boron nitride, aluminum nitride, beryllium oxide, magnesium oxide. There's a number of these different fillers that are utilized that have either higher thermal conductivity or other properties as well. But we're going to focus on the ones on the bottom. So let's first compare these with regard to abrasiveness. Abrasiveness is really important because in most applications, you're using meter mix and dispense equipment. If you're using an abrasive filler, you need to make sure that the equipment that you're using is designed to handle abrasive fillers. Otherwise, you're just going to destroy the piece of equipment. It's going to very quickly be out of calibration. It's going to be mixing off ratio. There's going to be a number of other issues. So understanding that and understanding that in most cases when you're looking at really high thermal conductivities, you're using aluminum oxide there on the left of that graph there, which has a very high Mohs hardness, which means it's a very abrasive filler. Typically, anything over 5 to 6 on the Mohs hardness is going to be considered abrasive. So your meter mix and dispense equipment manufacturer is going to want to know that that's in your particular system. Now, let's talk about the relative conductivity of these different materials. So I have on here the relative thermal conductivity and the Mohs hardness kind of side by side, right? So first let's talk about the thermal conductivity. So these are the thermal conductivities of polyurethane material at 76% loading, all right? Nothing special was done to these to really improve that. It's just, we threw it in there just to kind of give you an idea of how they compare. And aluminum oxide obviously is going to be the highest, and it's much higher, significantly higher. Almost 0.4 watt per meter Kelvin higher than any of the other fillers. And understanding that, it's important to understand that aluminum oxide, being though it's a higher thermal conductivity, it's also the highest Mohs hardness. So understanding that you're going to need to make sure that your meter mix and dispense equipment is designed to handle that. All right. So from there, let's look at the CTE of these different minerals that are used. All right. So this is actually the CTE of the specific mineral. As you can see, aluminum oxide is really low. We're going to talk a little bit about why this is important in the final polymer, but really it translates into the polymer also having a lower CTE, all right? And you see how these other calcium carbonates higher, aluminum trihydrates higher, but fused silica down here, you see how that is very, very low. So if you're looking for a combination of the lowest CTE you can get and the highest thermal conductivity, you're not always going to get the combination of those two things, because as we saw earlier, fused silica actually has a lower thermal conductivity. So there's a little bit of a balancing act that you need to look at when you're looking for certain properties in your particular polymer. As well as electrical properties. So electrical properties are really going to be dictated by the filler, all right, that are in there. So as you can see, calcium carbonate has a very high dielectric constant, whereas if you get down into ATH, you get down into fused silica, you're at the far right side of the graph of what a base unfilled urethane or epoxy are going to be. So understanding that the filler also has an impact on the electrical properties of a particular material. All right. So once we've chosen the particular filler type, how does filler loading have an effect on the specific polymer? All right. So first and foremost, viscosity. That's one of the greatest challenges that you have, right? As you increase filler loading, your viscosity is going to go up. All right. Just like making, I like to use the analogy of making pancakes, right? We've all made pancakes. If that gets a little bit too thick, we add a little bit more milk to it, or we add a little bit more water to it to thin that down. If it's too thin, we add a little bit more flour, that increases the viscosity. The same thing is true when we increase filler loading on a thermoset polymer, all right? So let's start off with looking at the 20 RPM viscosity. So as you see down here on the bottom, filler loading percentage, as the filler loading percentage goes up toward the right, you can see that also does the thermal conductivity. But as the thermal conductivity and filler loading goes up, so does the viscosity. So we start off on the far left, less than 5,000 centipoise, and as we increase to the right, we go up to a percentage of 80% filler loading, and we're upwards of almost 50,000 centipoise. Equally important is the 2 RPM, which gives you an indication of what the thixotropic index of a material is. And the thixotropic index is an indication of, or it's really the ratio of the 2 RPM to the 20 RPM, or the low shear to the high shear viscosity. It really gives you an idea of how well the material flows. The higher the Thix index, the less it flows. And I've got a little video I want to show you here. So in electronic potting applications, we're worried about how well a material flows in and out of different areas. So if you look on here, you see some small, very small little pinholes, some through holes. As this image comes back up to the top, you're going to notice how this flows actually up through those pinholes. So this material was designed to have a high thermal conductivity, but additionally to flow very well and really encapsulate and coat all those different components. So that way you have really good contact of the polymer, so that way you can conduct that heat away from that very efficiently, okay? So in doing that, we need to make sure that we're cognizant of the Thix index, based on filler loading. So as you see here on this graph, obviously on the far left, you have a relatively lower Thix index, and as you go to the right, your thermal conductivity and Thix index increases as we get to the far right. All right. So again, as we increase thermal conductivity, we have to increase filler loading to accomplish that, and that inherently increases viscosity. Now, there are some things that we can do to really reduce the amount of increase in viscosity, and we're going to look at that during this presentation. We're going to look at particle size distribution. Additionally, we can do things like adding to certain wetting agents. There are certain filler types that we can utilize as additive levels to increase that with at the same time not increasing the viscosity as much and maintaining good flow of your particular potting material. So hardness. So as filler content goes up, the hardness of the polymer is going to be more and more dictated by think about it, the rocks that are in it. You have these tiny little rock minerals that are in there. And as you increase that, more and more of the hardness is going to be an indication of those rocks that are in there, really. So in this graph here, you can see how hardness goes up with filler loading, okay? And how as filler loading goes up, thermal conductivity goes up, and your hardness goes up, all right? And this is going to be true for any class. So I have down here kind of a hardness scale, right? So if your base polymer is a Shore double O, let's say a Shore double O of 30, and you start to increase the amount of filler in it, that Shore double O is going to go up. Or same thing in Shore A. If your base polymer is, let's say 40, as you add higher and higher filler loadings, it's going to go up from 40 and be a higher hardness. So just something to remember, if you're looking at a base polymer of a certain hardness, as you increase filler loading, your hardness is going to go up as well, okay? All right, CTE as well, all right? So very similar to how hardness is increased, because you have these minerals in there, you have these little rocks that are in there. As you increase filler loading, the percentage of coefficient of thermal expansion is going to be more indicative of the mineral that you have. For those of you that are familiar with what CTE or TG are, I want to show you a little bit what that is. So what we have here is our TMA. So the TMA is a thermal mechanical analyzer. And what it does is it measures how a material responds to temperature over a temperature range. And how it works is it actually has, let me stop this video right here. So what you have here, you can see that little black square. So what you have there is you have the sample, right? And then it's sitting on a quartz table essentially, or the bottom, and then you have a quartz probe that's sitting on top of it, all right? And what it does is it's measuring the height. As that goes down into the actual thermal chamber of the TMA, so you can see there's frost around the outside of it. So we start off very cold. So we get it down in there, we get the temperature equilibrated, and then the instrument measures the height of that sample over a temperature range. And so this is the graphic representation of that. So as you can see on the far left, we're at minus 50 degrees C, and then we slowly increase the temperature, and it measures the height. So that first red line that you see on the far left is the coefficient of thermal expansion, or the expansion rate over that temperature range, right? As it increases to the right, you see at about 60 degrees C, that inflection point. We saw that inflection point when we talked about phase change. So that's the TG, or the glass transition temperature. So that's the point at which, on the left side of that inflection point, it's a rigid glass-like material. For those of you that know the Shore D scale, that would be on the Shore D scale. On the right side of that, that would be the Shore A scale, or soft, pliable type of material. And on that right side, you have a different CTE, which is typically higher than you do on the left side of that. So just understanding what the TG and how we measure coefficient of thermal expansion. But getting back into that and how that affects, how the filler loading affects CTE is this graph here, all right? So we start on the left side of that graph with 50% filler and a CTE if you see on the far left, of about 95 part per million, okay? As we increase filler loading going to the right, you can see our thermal conductivity increases, but also our CTE is decreasing because we have more and more filler in there that's having its influence on the expansion rate, because the CTE of the filler is much lower than the polymer. So as you have more and more of the filler in there, your CTE is going to go down, all right? All right. All right, tensile strength. So the filler loading also influences tensile strength because, again, very similar to the other examples, as you have more and more of these filler particles in the material, they're having a greater and greater influence on the structure as a whole, all right? So if we look at filler loading versus tensile strength, this first graph here, all right? So on the far left, we have 50% filler loading, and as we increase that filler loading going to the right, you see that the tensile strength up until about 70 it goes up a little bit, but then once you get above 70% filler loading, it really increases very, very quickly. And ultimately what's happening here is you're getting a greater and greater influence of the filler particles on the tensile strength of the polymer. And that tensile strength is going up because the tensile strength of the mineral is higher than the polymer. Conversely to that, you have less and less polymer, which is the elastic portion, all right? So as you increase filler loading to the right in this graph, you see a decrease in the elongation, all right? And the reason you're getting a decrease in the elongation in the blue line there is because you have less and less polymer, which is the elastic portion, and more mineral, which is the rigid portion, which doesn't have very high elongation at all. All right? And then electrical properties, right? So again, as we have greater and greater filler loadings, the electrical properties of the polymer are going to reflect more and more of the electrical properties of the mineral, okay? So, and the important thing to remember is all minerals have a little bit different electrical properties. We saw that we talked about filler type. Each filler type is going to have different electrical insulating properties, so it's really important to understand that if you want certain electrical properties, as we increase the amount of that filler, we're going to get certain electrical properties associated with that. So if you want really, really high thermal conductivity, and we have to use aluminum oxide, you're going to kind of be stuck with the electrical properties to a certain extent. Now we can adjust the polymer, and there's certain things that we can do on the formulating side, but the aluminum oxide is going to dictate a lot of the electrical properties that are in that final material, all right? So in this example, you have here, we have the dielectric constant versus filler loading of this material, and as you see, as we increase filler loading, you're getting a greater and greater influence of the dielectric constant and an increase based upon the filler that's in there, as well as the volume resistivity. So for this, the volume resistivity is actually going up as we increase filler loading because the filler itself has a higher resistivity, volume resistivity value in and of itself. All right, so we talked about filler loading. Now let's talk about particle size. So particle size is really important, and as a formulator, probably one of the most important tools that we have to really optimize the properties of a material when it comes to whatever properties the filler itself is really translating into the polymer, all right? Why is filler particle size important? Remember, we talked about how thermal conductivity is all about kinetics. And kinetics is contact of particles, how uniformly the particles are in contact, okay? So I have a couple pictures of marbles up here. So for example, on this far left picture here, we have these marbles. You see there's a lot of interstitial space in between them. They're all kind of not really uniform in how they're packed in here, right? So there's lots of space in between them. Versus the picture, next picture over here, very uniform, but we still have a lot of space in between each one of these. And if we're looking to increase particle contact, we really need to be able to have a number of different sizes of particles in the filler. So in this example, we have all these marbles that have all these different particle sizes, and you see how you get a much more tight packing, a lot more contact between each of those particular marbles. And ultimately, that's what we try to accomplish when we're formulating material. Now, how do we do that? Well, we leverage our master sizer particle size analyzer. It's a laser diffraction particle size analyzer. To put it simply, ultimately what it does, I'll kind of show you a little bit of an example here. So you'll see in this video, it kind of shakes the particles down into that center trap, and then it actually sucks them in through a laser diffraction analysis instrumentation. And it measures the average size of those different minerals in that particular sample. And what we end up getting is a report of the particle size distribution. So you see here we have particle size A, particle size B, particle size C. So each one of these is a different what's called mesh size or different average particle size. And then you have on either side of it, you have a little bit larger and a little bit smaller particle sizes associated with that. So when we're formulating a material, what we're looking to do is we're looking to accomplish a very similar appearance as you saw in the marbles earlier. We have really, really big ones, we have smaller ones and smaller ones and smaller ones, so you get really tight, intimate contact and really, really good packing between those, so you get really good particle size contact. So we're ultimately optimizing particle size distribution using different sizes in order to get that optimization of properties. And you're going to see a really, really great example of that in just a minute. So we'll start off with how that affects viscosity, okay? So let's look at, we talked about how filler loading affects viscosity. So all of these graphs are the same filler loading and showing how having different particle size distributions affects the viscosity and the thermal conductivity. So let's start off here with the 20 RPM, all right? So what you're going to notice on the far left of the graph, you have an average particle size of approximately, let's say around 50 micron. You see a relatively high viscosity. And as the particle size goes up, you see that viscosity goes down. But what's really, really interesting about this, I want you to look at the orange line. The orange line is the thermal conductivity, all right? You see how we have a big hump in there, right? And what that's showing you is that's showing you how in this particular material, when you have an average particle size of about 150 microns, you have an optimization of the thermal conductivity, right? If you say, well, if we just put lots and lots of small particles in there, we're going to get better thermal conductivity, so we're going to have better contact, better thermal conductivity. That's actually not true. If you look on the far left, right, when you have a very small particle, you actually have a pretty low thermal conductivity, almost just above 1.08. Whereas if you actually increase your particle size a little bit and get to an average particle size of 150, you actually increase your thermal conductivity and reduce the viscosity at the same time. Additionally, as we were talking about earlier, talking about process and flow and Thix index, you see the same kind of thing in the 2 RPM, right? So in the 2 RPM viscosity, you see very small particles. We have a very high 2 RPM viscosity. As that average particle size gets larger and we get to 150, again, we have the optimization of the thermal conductivity in the orange line, and then that 2 RPM viscosity actually drops. And we also see that down in the Thix index, right? We actually see the Thix index go down when we get to that optimization of that 150 average particle size, okay? So if you take nothing else from this presentation, understand that particle size distribution and optimizing particle size distribution is really, really important when you're trying to optimize thermal conductivity and viscosity. So now we'll talk about electrical properties, all right? So it's also important to understand that also has an effect on the electrical properties of a particular material. So when you're talking about particle size, you're going to have some particle size distribution effects on the electrical properties. As you obviously have different particle sizes, you're going to have different ability and different contact. So when you have different particle contact, that's going to have an effect on how the that material insulates a electric field between the two sides. When you're looking at a capacitance, for example, when you're looking at dielectric constant. Okay. All right. So from there, I'd like to kind of just do a general overview of these different properties and what's really important, the really important takeaways from what we talked about today. So, for example, I want to say ultimately that as thermal conductivity increases, CTE is going to decrease. And again, this is because we have higher amounts of mineral in the particular polymer material. As you increase the amount of filler that you have to increase thermal conductivity, you're going to get a greater and greater influence of the mineral on the coefficient of thermal expansion, all right? Same thing on the hardness, right? When we're looking at hardness, same thing is going to happen. Hardness is going to increase as we increase thermal conductivity, mainly because we have to increase filler loading. Again, this is really, a lot of this is coming down to how many filler particles do we have in there, and how is that influencing, how is its hardness influencing the hardness of the polymer. Again, increasing thermal conductivity, we have to increase filler loading to accomplish that, and that increases viscosity. Now remember, we can optimize that. We specifically talked about particle size distribution. We can also use different types of wetting agents. We can use a little bit different polymer structure to improve wetting on the surface of those particular particles. So, but generally speaking, when you increase thermal conductivity of any material, you're also going to have an increase in viscosity, all right? Also tensile strength, right? Very analogous to what we talked about as hardness. As we have more and more mineral material in a particular polymer, we're going to have a greater and greater amount of that influence of the tensile strength of that particular mineral. And conversely to elongation, right? We have less and less polymer in a particular material when it has higher filler loading, and that higher filler loading is decreasing the amount of elastic material, and it's decreasing the elongation of the material in the end. So, all right, and then let's talk a little bit about some different products that we have here. There we go. All right, so let's look at this graph here. All right, so as we look at, for example, 7566, that's really an EV motor application. Very good, nice high thermal conductivity, 2.1 to 2.25. This is a shore A material, so we have a kind of on the higher end of the shore A scale. Glass transition temperature of about -15 to 10, low CTE. So you see again that low CTE of 25 to 40 part per million. Again, that's dictated by the filler loading that we have to use. Really good electrical properties, tensile strength as well. Okay. Getting into power electronics, almost 3 watt per meter Kelvin on the next one down, 7591. Again, higher thermal conductivity, we're getting a higher viscosity. So you see that's 100 to 125, 150 centipoise. This is a shore D material, so that higher cross-link density is also influencing that as well. Battery application 7242. Again, this is a little bit lower thermal conductivity. So being a little bit lower thermal conductivity, that has a little bit lower filler loading. And you're seeing that actually, if you look at the CTE is higher than the previous two. So that's giving you that indication that there's less filler in there. So you're not getting quite as high of a thermal conductivity in that particular material. And then in the LED material there, the next one down, the last one down, 1.33 to 1.37. You see that has a lower coefficient of thermal expansion, and that's, again, based upon that filler loading. This is just a small sampling of some of the products that we have here available at Epic Resins. Again, like I talked about in the intro, we have a number of different products, and not only that, but we have the ability through our development chemists to fine-tune these or develop a brand new product that might be important in your application. So with that, I'd like to thank you all for joining us. We really appreciate your time. And if you have any questions, we have our contact information right here. And again, thank you all for joining us. Have a wonderful day.